In this video, we're gonna study symmetric orthogonal polynomials. We will show that when we have a symmetric orthogonal polynomials, then there are two families of orthogonal polynomials, which we will call even and odd polynomials. And we will find their three-term recurrence relations, moments, and then we will also prove the results using combinatorics. And finally, we're gonna show some connection with continuous fractions. Okay, so first let me define symmetric orthogonal polynomials. But let's recall that linear functional L is called is symmetric if all odd moments are 0. That means L of x to the 2n plus 1 vanishes for all n. Okay, and we say that so suppose that we have a monic OPS. So monic OPS for a linear functional L, then we say that this this is symmetric if L is symmetric. So in other words, odd moments of the orthogonal polynomials are 0. And in fact, we proved earlier that there are some equivalent conditions. So let's suppose that P and X monic OPS for a linear functional L, then we have equivalent conditions. L is symmetric, but of course this is 1 prime. Let's say P and X symmetric, they are really the same. And second, Pn, if you plug in minus x into Pn, then you get the sine minus 1 to n P sub nx for all n greater than or equal to 0. And finally, the recurrence, return recurrence, has a 0, Bn equals 0, so we can write in this way. For all n greater than or equal to 0, yeah, as usual. So we have these three equivalent statement for monic OPS to be asymmetric. So now suppose that we have a monic OPS symmetric. Suppose that this is symmetric. And we have this three-term recurrence. With, let's say, a linear functional L, as we had all setting here. And by the theorem, we have, if you look at P2n and minus x, then this is by the theorem, this is minus 1 to 2n P2nx, but of course this is P2n of x, and P2n plus 1 minus x is, if you do the same thing, then you get minus sign. That means this polynomial P sub 2n is an even polynomial, and P sub 2n plus 1 is an odd polynomial. So that means we can write p2nx. This is because this is an even polynomial. We can write this as e sub n of x squared for some polynomial en, and p2n plus 1x equals x times on x to the x squared, where enx, onx, these are polynomials. Okay, so we can write it this way, and we say that these polynomials, this polynomial sequence, these are called even polynomials for p, for this Pn. And these On, we call them odd polynomials. Okay, so we have even and odd polynomials associated to an OPS. This is, of course, when this is symmetric. And we will show that they themselves are also orthogonal polynomials. So to do that, we're going to introduce linear functionals. So define L of E, linear functional L of E, L of O in this way, L of E of f of x for a polynomial. This is just the original linear functional applied to f of x squared. Because this is a polynomial, we can evaluate this, and that's the definition of this. And L of O, f of x is defined similarly, x squared, f of x squared, like that. So these are the definitions. Actually, we need a factor here, 1 over lambda 1. The reason why we have this factor is that we want them to be linear functional that sends 1 to 1. So note that L of E1 equals 1. L of 1. Oh, by the way, we assume here, okay, we're gonna assume L of 1 equals 1. Yeah. So L of 1 and L of O1 equals 1 over lambda 1, L of x squared. But x squared is the moment, 2nth moment, but we know that there's only one dict path, because bn equals 0. Lambda we only have up steps and down steps in our Machkin path. So we have up and down, and this has weight lambda 1. So this is 1. And this is why we divide this by 1 over lambda 1. All right. And also we define the moment, the notation, mu and E equals the moment for this linear functional, and mu and O, of course, is the moment for this linear functional. Okay. And a nice theorem is that even polynomials, this is an OPS for this linear functional, and odd polynomials, they are monic, by the way. And moreover, also mu, you can evaluate, we can compute this. This is the 2nth moment, and maybe I can write it here. This is 1 over lambda 1 mu 2n plus 2. Okay. So proof. Proof is actually quite straightforward. So we know that this is an OPS for the linear function of L. So we know that L of Pn Pm equals delta nm kn, where kn non-zero for some constant kn. So we can just show the orthogonality of the even polynomials using the definitions that we have. So this, by definition, L of we replace x by x squared, so x squared. But En is p 2n, where this just by definition of En. But of course now it's just a product of two orthogonal polynomials. So they are equal means like n and n are equal, so we can write it this way. But this means that orthogonal, these orthogonal OPS for L of E. And similarly, we do exact same thing, OM. Now this is 1 over lambda 1. We multiply x squared because of the definition, L of x squared on x squared om x squared. But by definition, x times on x squared is pn plus p2n plus 1. So this with only one x gives us 2n plus 1 p sub pn plus 1, and the remaining x together with om we get p2n plus 1. So this is going to be equal to L of p2n plus 1 p2m plus 1. But then this is 1 over lambda 1 delta nm k 2n plus 1. So again, this is linear. We show this shows that this is an OPS for L of O. Now we proved these two statements, but these are remaining, so let's compute them. And mu and E is by definition L of E of x to the 2n. Sorry, x to the n. But this, by definition of where is it? Here. This is L of x2n, but this is mu 2n, as this is a statement that we wanted, and O is 1 over. Sorry, we should write this first. This is the definition of mu and O, but by definition of the L of L super O, this is lambda 1 L of x squared times x2n. But of course, this is 1 over lambda 1 mu 2n plus 2. So that is the end of the proof. Okay, so this theorem tells us that the even and odd polynomials associated to symmetric orthogonal polynomials are orthogonal polynomials. So they must satisfy three-term recurrences. We will find the three-term recurrences now. So theorem. E2 n plus 1 x minus equals x minus lambda 2n minus lambda 2n plus 1 e n x minus lambda 2n minus 1 lambda 2n e n minus 1x. And on has a similar recurrence, but the indices are shifting. Like this, minus 1. Okay, proof is also not difficult. we can use the three-term recurrence for the original polynomial, where it is. Yeah, here. So if we replace, so we just substitute 2n here, and 2n, we will consider 2n and then 2n plus 1, or 2n plus 2 there. And then we get recurrences like this. p2n plus 1 x equals x p2n. This is the recurrence for Pn. And p2n plus 2 is this. But now here, from here, we're gonna multiply x for the first recurrence, just to make sure that that's what we want. Oh, sorry. Oh yeah, I think that's right. Okay. Now, then this is on, right? So this is on, but x squared equals, this part is en, x squared en, x squared minus lambda 2n, and this part becomes on minus 1, right? And this is en plus 1 of x squared equals, but this part is on minus lambda 2n plus 1 en of x squared. Now from here, we can replace x squared by x, then we get exact same thing. I think I can just copy this whole thing. I'm gonna just remove all the x squared, like that. We can do this. All we need to do is to solve this equation, or we know we can write O in terms of e's. So if you plug in O over here and there, then you get recurrence for en. And also if you write E in terms of O's and then plug in the formulas there, you get a formula for recurrence for O. That's it basically, just to replace, for instance, from this we know that, okay, let's begin. From this we know that on, let me omit the x there. On equals en plus 1 plus lambda 2n plus 1 en, and from this I'm going to keep en with x equals on plus lambda 2n on minus 1. So if you plug in say this into this, then see what you can get. Then you get xen equals en plus 1 plus lambda 2n plus 1 en for on, lambda 2n. But now here you have to replace n by n minus 1, so en plus lambda 2n minus 1 en minus 1. Now you rearrange these to get en plus 1 equals, we have en, we're going to move all the en's other side, and then we get x minus lambda 2n minus lambda 2n plus 1 en, and finally this, we get this, which is exactly the first identity or recurrence. We can do the same thing. We now write this in terms of O and then plug in over there. But because we have x, we first multiply x everywhere and then use this formula. Then we get x on equals, now this is x en plus 1, so you multiply, you replace n by n plus 1, so on plus 1 plus lambda 2n plus 2 on plus here we have x here, so we multiply these two, so lambda 2n plus 1 on lambda 2n on minus 1. But now if you rearrange as before, we get something like this. But this is exactly the recurrence that we wanted. So that's the proof. So it's just a computation, nothing serious. So now that we have a recurrence, three-term recurrence for E and also for O with these recurrence coefficients, we can write down the moment of E and the moment of O in terms of generating functions for Mochkin path with weight given by these quantities. So I'm gonna write that down as a corollary. So let's say lambda k greater than or equal to 0, a sequence, but we somehow want to keep lambda 0, 0 because when we for lambda sequence we only need lambda 1, lambda 2, etc. We don't really need lambda 0, but we put this to be 0 because in our formula lambda 0 appears, just to make it more recognizable, to become a recognizable pattern. So, and then we're gonna define sequences. Let's say this O, boldface O is as a sequence of BK. So this is basically a sequence of zeros only. So the boldface O means a sequence of zeros. And lambda, a boldface lambda equals this lambda k greater than or equal to 1. And B, boldface B super E is the sequence that we have here. So this is going to be BE, lambda E, BO, lambda O. That's what I'm gonna write. Lambda 2k plus lambda 2k plus 1, index from 0, 0, and lambda E, lambda 2k minus 1, lambda 2k from k from 1, and then BO, lambda 2k, 0, all shifted by 1, the above thing, except they're all shifted by 1. Note that lambda 0 appears here, so if k equals 0, this is lambda 0, but we ignore that because that's going to be 0. Okay, that's why we want this. Then the moment of this is the original moment with B sequence and lambda sequence, and this is equal to mu n BE lambda E, and mu 2n plus 2, this is equal to lambda 1 mu n BO lambda O. Okay. Why is this true? Because this is the moment. This is basically where is it? Yeah, that's basically this. Because this means that the moment, this is the weight generating function, generating function for Mochkin path, where the weights are given by these. That's what this means, right? And that is equal to this, which is the generating function for Dick path with weight given by this, but that's this. So that's basically the proof. So nothing extra information we need. All right, so now we have these even and odd polynomials, their recurrences and moments like this. But when we see this, we may wonder if we can prove this combinatorially, because everything is explained completely combinatorially. Generating function for dict path, generating function for Machkin path, where the weights are somewhat different, and same here. So in our next section, we're gonna prove this combinatorially. Okay. So section 9.2, converting dict path into bicolored Machkin path. Okay, so we need some definition. A bicolored Machkin path is a Machkin path except in which every horizontal step is colored red or blue. Okay, so like up, horizontal, down, horizontal, up, down, something like that. So, and we're gonna use U for up step, D for down step, HR for horizontal, red horizontal, HB for blue horizontal. Okay, and there is a simple bijection between dict path and bicolored Machkin path. So let me explain. Oh, I need to introduce one more or two definitions. And Mach n of 2 is the set of all Machkin path bicolored from 0, 0 to n0. Okay, and I'm gonna use one more notation. This super 0 and 2, this means set of all elements in Mach n2 where such that pi has no HR on the x-axis. So height 0. The height 0, I think no, it should be s. So that means, in other words, height 0 horizontal steps is always red. Okay, like this. We cannot have blue in this set. That's the definition. Okay. And now I'm going to define two maps from Machkin path. So first, let pi as a step s1 up to s2n be a Machkin path of length 2n. So we have 2n steps like this. And then we're gonna define pi phi1 of pi to be a Machkin path, Machkin n super 0. So that means horizontal steps always on the x-axis always red. In the following way, tau is t1 dot 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 tn, where what is ti? This is, we have four possibilities: t, u, d, h, r, h, b. If the s 2i s 2i plus 1, s 2i minus 1 as 2i equals uu, and if this is ud du. So in a diagram, or if you want This means that, like, this is up, up, down, down, up, down, down, up. Okay. So for example, maybe I can show you an example. Like this. Yeah, so this is our dig path of length 2n, n equals 8. And so we separate the steps into 2 steps like this. So we combine the first two steps together and the next 2 steps together, etc., by separating the path using these orange vertical lines. Then if this is up, up, then just change it into a up step. So now this is our Munchkin path. So 2 steps become a 1 step. So this is 1 up and down, down. So it's down. Up, down becomes up, up, up. So up, 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 down, 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 up. Horizontal, but blue horizontal. And down, down becomes down. So here I think this should be lambda 1, lambda 1, lambda 2. So this becomes this. This is clearly a bijection. And you see the down steps here. If you have down, down, their weight multiply like this. But if you have up, down, you have one down step with weight lambda 1 here, going down over here. This, we take the product of them. Down step becomes the weight of this just moves over here and like this. So this is clearly a bijection, and you can see that horizontal step at the bottom cannot be blue, because if this is blue, that means we have down, up, but we cannot go down at level 0. So this always is up. This must always be up, down, so it's a red. But this is okay because you can go down or up. So this is really a simple bijection, and we can do similar things in this way. So now let pi is now s1, s2, s2n plus 2 in dig path 2n plus 2. Now we're gonna define feed 2. I think this was v1, v0, sorry about that. This is v1 of pi is tau, but this is in Munchkin path n of 2. Now we don't have 0 here, so here, but we have a 0. But this becomes this, where tau equals t1 dot 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 tn, where ti is defined exact same way, u d h r h u, but here s2i plus 1 equals uu dd ud du, like that. Up, up, down, down, up, down, down, up. Again, I'm gonna just give you an example. This example will make it clear that this is gonna be a bijection. So like this. But the difference here is that we ignore the first step and the last step, and then we divide the remaining steps into 2 steps like this, and we just change 2 steps into a 1 step depending on these cases. So yeah, I think blue and red are yeah, this is wrong, so let me correct them. This is red, this must be blue, this is this is okay. This is okay. Down up down. This is okay. Down down up down. Yeah, this is okay. Only these two are wrong. And this is also a bijection because now, because we are already here, the height is 1, so we can go up down or down up. So we even at the level 0 we have both red horizontal and blue horizontal. They both can appear like this. So combining these two bijections, or just by the two bijections, we can write down this theorem. The map phi 0, this is a map from dict path to margin path, and phi 1 dict path 2n plus 2 margin path of size 2. Then these are bijection. Such that if phi 0 equals pi, if this is tau, or maybe I can write it here. If we have this, then what is the relation between the weight of pi and the weight of, okay, I think I need more space. Such that, let me rearrange the formula, weight of a tau, where we use P E lambda E, and if we have this, then the weight of pi is lambda 1 times weight of pi, tau PE, O lambda O. So this should be clear if you understand the bijection. So this becomes this, so this is the basically lambda E like this. And this, because we have, for horizontal step, we may have red or blue for some horizontal step, but red and blue, they both give this and this. Okay, that's why we have a plus here. And that will give us proof of this, and this is exactly the same, except that we have to multiply lambda 1 because we ignore the first and the last step, but this has no weight, just weight 1, but this has weight lambda 1, so we have to multiply lambda 1 over there. So that's really the proof. Yeah, so simple bijections, they give proofs of the fact that the moments are related. So I'm gonna write down the corollary. This corollary, we have this. Where is it? This. Maybe I can write down this. So this gives us another proof of, yeah. Okay, we have a combinatorial proof. Now let's move on to the final section in this chapter. This is about continued fractions, two types of continued fractions that we'll call J fractions and S fractions. So an S fraction, also called steel chest fraction, is a continued fraction of this form. Continued of the form 1 over 1 minus c1x over 1 minus c2x over da da da. Okay, and a j fraction or a Jacobi fraction is a continued fraction of this form, 1 over 1 minus b0x minus lambda 1x squared over 1 minus b1x minus lambda 2x squared over da da da. Okay, and actually we know that this is equal to the moment. As a generating function, if you write this as a generating function n greater than or equal to 0, x to the n, this part is the generating function for dict path, all pi in the dict path of length 2n, the weight of pi like this, c, where c, this means like c1, c2, this sequence. And we know that this is generating function for all Matchkin path. B and lambda x to the n. Yeah, we proved this in the Flageolet's theory of continued fractions. So, because we have C fractions and S fractions and J fractions as generating function for dict path, Matchkin path, but these are really moments of some orthogonal polynomials coming from these sequences. So because of that, we have this nice connection between the two continued fractions. So the statement is the following: 1 over 1 minus lambda 1x 1 minus lambda 2x equals 1 over 1 minus lambda 0 lambda 1 x minus lambda 1 lambda 2 x squared over 1 minus lambda 2 lambda 3 x lambda 2 lambda 3 lambda 4 x squared over dot dot dot. So this continued fraction, this is equal, and also this is equal to 1 plus lambda 1 x 1 minus lambda 1 plus lambda 2 x minus lambda 2 lambda 3 x squared over 1 minus lambda 3 lambda 4 x minus lambda 4 lambda 5 x squared over dot dot dot. So this is a s fraction, but this is a j fraction. Also, this is a j fraction, or this part, if you look at this part. And these, by the way, here we assume that lambda 0 equals 0, because we actually don't need a lambda 0, but to make this in a nice pattern, I included lambda 0 here, but lambda 0 is 0. Okay, proof is really just combining the results that we already know. And the left-hand side, this is equal to generating function for all dict path. Zero and lambda x to the n, like I said, by the Flageolet's theory. But this is equal to, this part is the generating, this is really mu 2n, 0 lambda. Okay, and let's say this is 1, this is 2, and this is 3, just to make it clear. So this is 1. 1 is equal to this. What about 2? 2 is equal to generating function for all Mochkin path where weight is, so these are the b's and then these are the lambdas, but this is really the be that we defined before, lambda e x to the n. But we know that this is mu n be lambda e. But we know that these two are equal because they are equal. So that proves 1 equals 2. And for the third one, we know that 3 equals sum over n greater than equal to but before directly writing 3, let's look at this first. We know that lambda 1 mu n bo lambda o x to the n, this is equal to mu 2n plus 2 0 lambda x to the n. We know this times this is equal to this. That's one of the theorems that we proved. And now if we look at this starts from the index is not from 0, but the index starts from 2. So 2, 4, etc. And this is somewhat off. So this is like x inverse. So this can be rewritten 1 over x sum over all n in our usual form. If you write it this way, then you have to subtract 1 because if this is 0, that part doesn't exist here. So we can rewrite it this way, and then finally we can rewrite this. Then we get sum over n mu 2n equals, we multiply both sides by x and then move this, then we get lambda 1 mu n bo lambda o x to the n, like this. Sorry, x should be there. But what is this? This is like Mochkin path 1 plus lambda 1 x summation pi in the Mochkin path, a weight of pi bo lambda o x to the n. But this part, if you think this part here, this part is exactly 1 over this part over here. Then this proves that this is 3. So this is 3. But this is what? This is 1. So we proved that 1 equals 2 and then 1 also equals 3. So that proves the all identities. Yeah, that's the end of this chapter.